at question number 5 and tutorial sheet number 7 is under rotational motion. And in this question, we've been given this sphere, a solid sphere, and this hanging mass here. So we have this scenario where this hanging mass is covering or encompassing two concepts, where it is rotating, and as it rotates from this end, as it rotates, it is covering some linear distance or some linear displacement as it falls. So it is encompassing two concepts. And the question, the information that we have is the mass of the sphere is 2 kg, the falling mass 800 grams, then the height at which, or the height it falls is 1.5 meters. The radius of a sphere, that is 30 centimeters. And for a solid sphere, the moment of inertia is given by 2/5 mr squared. So we are going to proceed as follows. For the first part, which is part A, as this mass is falling, it is covering the linear displacement or linear distance. Then, as it is coming from this side, it is also rotating as well as covering some distance. So from this point, it is so much important that we know how the energy changes. And in this question, we are going to use the principle of energy conservation. We know that potential energy must be equal to kinetic energy total. Why kinetic energy total? It is because there is rotational kinetic energy and translational kinetic energy. Because as it comes from this side, it is rotating this way. It is just covering linear displacement. So for this, we know that PE, potential energy, is given by, since it is just under the influence of gravity, it is just mgh will give us. So kinetic energy we have for Ke, kinetic energy rotational, plus the kinetic energy translational. So this is what we are going to work with. But we know that I, which is moment of inertia, is equal to this. So let me erase the first part. mgh is equal to half moment of inertia omega squared plus half mv squared. So we know that I is equal to this, and from the same, we know that this is equal to r times omega, where for omega it is v over r. So putting this and this in this equation, we are going to have mgh is equal to, so from this we are going to have mgh is equal to this, and this will cancel. So we are going to have mr squared over 5 times, so this will be v squared over r squared plus half mv squared. But r and r can also go, and we're going to have mgh is equal to m v squared over 5 plus half mv squared. Since v squared is common, we can even factor it out. mgh is equal to v squared capital M over 5 plus small m over 2. Putting in the values, we have for the falling mass, we have 0. Okay, we have mgh is equal to v squared times, so this one is 2 over 5 plus 0.8 as the mass for this for falling mass over 2. So this one we're going to have mgh, and the common denominator here is 10. 2 into 5 into 10, it is 2 times 2, 4, plus 2 into this, it is 5 times 0.8, it is 4. So we have mgh is equal to, which will give us mgh is equal to 8v squared over 10. So 8v squared is equal to 10 mgh. From this point, we can divide through by 8, also here by 8. So that v squared is equal to 10 mgh over 8. So putting in the values of 10 times, so this one we are going to get 14.7 v squared. So introducing the square root to both sides, we're going to get v is equal to 3.8 meters per second. So this is the value for the velocity of the falling mass. Now we can go on to find the momentum. So the first part, which is A, the value is this. Angular momentum is given by I omega. Okay, so L is equal to I is 2 over 5 m r squared omega times this one, it is the angular velocity is equal to v over r, so which will be 3.8 over 0.3. So we have one. This will give us 0.91 units kg meter squared per second. So this is the angular momentum of the sphere.